the unfortunate situation that a BB bar background like this, because of its large cross section, goes far above the peak. There is a peak, but this peak will never show up because the magnitude of the background is too large. There are too many BB bar produced, and accidentally many of them will occur at the precise point where we have the Higgs invariant mass, or the mass of the Higgs. And therefore, the enhancement due to the branching ratio of Higgs going to BB bar is worth nothing, because it will be swamped by the background. Therefore, the point is that if you have a signal which involves strongly interacting particles only strongly interacting particles, like Higgs going to BB bar, there is nothing else, then you be very careful about the future of the signal, because other strongly interacting, as the name suggests, the strongly interacting particles will be produced with large probability, and in that case the noise can swamp the signal. That is, the noise is too big compared to the signal. On the other hand, if you have photons or leptons in the signal, then of course they will also have background. It is no secret that they can also be produced, but they are probably manageable. And in the case of the lower one, it has 4 leptons. So having a 4 lepton from a standard model process itself is small, as you can see from the low background here, except for this one which is coming from the Z. But you have the background, these are the background processes, I will explain that, is in general manageable. So this is why we decided to take. So what is the lesson of this exercise is that cross section times branching ratio is not the whole thing. The important point is the signal, the final event that you are going to detect from your new particles. And if that signal involves particles which will be naturally produced in the LHC environment in large numbers, then background will obviously completely dominate over the signal and you have nothing. Okay. Now,
so sir, whenever we are looking for a discovery, we first we know what are the things colliding, and we just only know the stable particles in our detector. Everything in between is a black box.
That's a theory.
It's a theory basically. So when we decide, okay, we are seeing some event where we have 2 photons or 2 jets, so we just keep those information, and then we know what are the things colliding with what energy. Then we go back to our theory to
except for the case when you see an invariant mass, which shows that the mass of the mother particle is not agreeing with standard model particles. In that case, you know, whatever be the theory you do not know. You cannot say that we are seeing supersymmetry or exotic leptons or something blah blah blah. You can say that we have seen something new. That is the beauty of a peak. But now what we are trying to do is we are trying to say that the invariant mass peak is coming from a standard model Higgs. In order to understand that, we have to now churn our theory machine. What is the cross section? What is the branching ratio? In fact, the experimentalists do the churning, also the phenomenologists, before the discovery, and see which channel looks promising. That is, in which channel signal is big, but that itself is not the whole story. What is the background? And if they find that the background is manageable, then one goes for this.
And sir, just to keep this manageable word, like
Yeah, I'm coming. Of course, manageable is what? I'm coming to that issue. But before we go to that, let me then see that if I summarize what we have said so far is that so far we have seen that the number of events is proportional to the production cross-section and the branching ratio. If you are trying to discover Higgs, F means some final state. We have seen two examples. The final state could be gamma gamma, 2 photon or 4 L. So this is a very important quantity. It is a proportionality. I will show you soon how we can write it down by an equality, not the proportionality. However, our discussion during the last 10 minutes show that this cannot be the final story because if this was the final story, then you would conclude that Higgs produced by some mechanism multiplied by its branching ratio into BB bar is the best
choice.
option. But that is not so, as I told you, simply because the background in that case is too large, because BB bar production cross section itself is too large. So therefore, we have to do something which is called kinematical selection. That is, we have to select certain kinematical selection means feature of the final state if this determines what your signal is, and this feature comes from kinematics. That is why the kinematical selection. That is, you need not know the production cross section, you need not know anything. For example, a invariant mass distribution is a fine kinematical selection. That is, I accept only photons which are within the window around the Higgs mass or the mass of the produced particle. The mass is, of course, what its mass is, and the width is determined by the total width. So that itself is a kinematical selection. That is, you tell yourself that throw off all the photons whose mass is not there. Now I will come to another example, just to tell you, we will talk a lot more about kinematical selections later on, which is a good selection, which is a bad selection, so on and so forth. But let me just give you one thing which we can understand by common sense. Like suppose two particles are colliding. Now from our daily life, just think of the collision of two marbles. And what we see? Well, normally they will more or less follow the trajectory. Only if they are very energetic, they struck into one another very hard, then the outgoing marbles, here no new particle production, nothing. The outgoing marbles can go with large transverse momentum, that is momentum perpendicular to the initial momentum. And therefore, we say that hard scattering, now this hard scattering is a term which generically means that, which leads to hard transverse momentum of the scattered particles. So hard scattering means that Pt of the final state particles are large. Now this of course from our common sense, that we know that when two particles hit into one another, large Pt is not natural. Okay? If we put in another language, we will say that in most cases the cross section, the scattering cross section of a final state with large transverse momentum is small. Now what is the other way we can have particles in the final state with large Pt?
So what did you say last sentence?
See, when two particles scatter, normally if the scattering is low energy, it is expected that the particles will follow more or less the initial direction. So the line of the particle beams. If it is a high energy scattering, only then we expect particles to have large Pt or large transverse momentum. But what is the other case? Now quantum mechanics come into the picture. That is, by the way, remember this notation. This Pt means transverse momentum. P in my notation will mean momentum in general, and then the momentum can be divided into two cases. One is along the incident direction, or in the case of a collider, along the direction in which the two colliding beams move, and Pt is perpendicular. So final state with particles having large Pt may come in and what is that way? Well, now I think the way is clear. That is, suppose you are colliding two particles and you have a particle which is produced almost at rest, but nevertheless it has a large mass. Okay. So you produce a large M particle produced. Now since this is very massive, as I told you, it will decay promptly. Now of course the decay will have a distribution, but for the sake of simplicity let us assume that the decay is isotropic. That is, the decay products, and also for simplicity let us take it is a two-body decay. Then for simplicity we consider this situation that particles will come out in all directions with equal probability, right? What will be the Pt? This can be decided from energy momentum conservation, because initially we have a heavy particle at rest. Therefore, the mass of the heavy particle should be equal to, if it is a two-body decay, its mass will be equal to the energy of particle 1 and particle 2. Now what happens? It is as probable as having a longitudinal momentum which is large, m is large, so mass over 2 is also large, assuming that the two produced particles are identical. Then if a heavy particle is produced, then its decay product is as likely to have large transverse momentum as the longitudinal momentum. Okay? On the other hand, what is the background? The background is like run-of-the-mill scattering. An intermediate state heavy particle is not there. Like PP colliding and we have a BB bar. Now this BB bar, of course, some of them will have large PT, but in most of the time it will have small PT, but in some cases it will have large. So to summarize then, if we typically look for a PT distribution, this is not a particularly precisely drawn figure. I am just plotting something to convince you that PT is a way of distinguishing. So here we plot PT distribution, and here we plot number of events. Now the number of events in which one of the particles have high PT coming from the decay of a heavy particle is likely to be something like this. That is, it has a peak at a, so I call this PT of the signal. Again I remind you that this is not a precisely drawn thing, it is just a qualitative description. Whereas the PT distribution of something which is not coming from a heavy particle, just from scattering, okay, no intermediate heavy particle, it is going to be something like this. I mean, it will be peaked at low PT and then it will be falling like this. Now there is a catch. You see what this means? I am not saying that it is sharply falling to zero. So this is the PT of background. Now it is not sharply falling zero. We have this, what I call a tail of the distribution. That is, it is going to zero but very slowly. Okay, maybe for very large PT which is not allowed by kinematics. There is also a thing called kinematics. You know that kinematics is that for a given process there is a restriction on energy and momentum. So obviously there will be a restriction on the PT of a particular particle. So it cannot go to infinite values, but the fall would be small, and this is again a game of probability, because quantum mechanics will never tell you that PT is precisely zero at some intermediate value which is less than the kinematical limit. But remember, the cross section of the noise is large. So if you say that the probability of PT is high PT is small, so the probability of high PT multiplied by a large production cross section still can give you a sizable number of events. On the other hand, the background is naturally have a sharp PT distribution which is peaked at a high value of PT compared to the background, but its production cross section is small.
That is signal, no?
Signal, sorry. This is PT of the signal, the
Right.
sharp one is
Signal.
PT of the signal and the other one is PT of the background. But you can always say, just like invariant mass, you said that I select events which peak at a particular mass. You say that I select PT, let us say greater than this value. So there is some value